Hi, my name is Emily, and today I will be explaining the mass spectra, IR spectra, HNR, and CNMR for DDT. This is the mass spectra for DDT, and we have a formula of C14, H9, Cl15, and the molar mass of DDT is 352, so we have our M plus peak right here at 352. We have our base peak right here at 235, and when you subtract those two, you get 117, which is not, it doesn't represent any fragment. And if we look beyond the base peak right here, this peak's at 124, and that doesn't give you any information either. For our degrees of saturation, we have 2 times the number of carbons, plus 2, plus any number of nitrogens, which we have none, so 0, subtracting the number of hydrogens, which is 9, and subtracting the number of any halogens, which we have chlorine right here, and there's 15 of them. That's going to be all over 2, and that gives us a degree of saturation of 3. So it's either going to be 3 rings or double bonds. Okay. And that is all for mass spec. Here we have the IR spectra of DDT, and I already have our zones labeled out, where this is zone 1, zone 2, zone 3, zone 4, zone 5, and the fingerprint region. So if we look in zone 1, we don't really have anything. So we have nothing. And in zone 2, we have this peak right here at around, it's between 3,000 and 2,900. And then we have this little one right here, which is between 2,900 and 2,800. And these are both indicators of alkanes and aldehydes. Now, let's move to zone 3. We don't have anything. Zone 4, it's the same thing, so both of those are nothing. And as we come to zone 5, getting around 1,500, this peak is an indicator of aromatics. It's an aromatic stretch. Which means we will have some rings. And this other peak right here is just an indicator of alkanes. So now we go into the fingerprint region. And remember again, our formula is C14, H9, Cl15. So we have this small little peak past the 50, but based on what our formula is, that's not going to give us anything. So then we look at this peak right here. This is actually, this peak doesn't give us anything, and then these two peaks, again, when looking at our compound, don't really give us anything, because these are indicators of having any oxygens or nitrogens in the compound, and we don't have that. And when we look right here, this is around 850. This is an alkene bend, which is just an indicator of alkenes. And right here, this is rounds 800 to 750. These are alkyl chloride stretches. Anything between 850 and 500 is an alkyl chloride stretch, which that matches with our compound. We have chlorine. And then we look at this peak. It also, in addition to being an indicator of an alkyl chloride stretch, it's also an indicator of an alkene bond. So this is the proton NMR, and before I do anything, the first thing I'm going to do is write the integration numbers. So for all of these, they have an integration of 1. So with our IR, it told us that we're going to have some alkanes, alkyl chlorides, aromatics, and alkenes. So let's see. Let's start drawing the structure. So we have chlorine, carbon, Now, with this HNMR, you're going to notice something very interesting, because as you can already see before I'm even finished drawing the structure, it's pretty symmetrical down the middle. Let's finish this. Okay, so as you can see, you can actually, let's do it right now, draw a line down the middle, and it's the same on both sides. So this HNMR actually only shows the hydrogens on one side, because all the hydrogens on this side are the same as the hydrogens on this side. We also have an H here, just make sure you still see it. So now we're going to see which hydrogens are which, and we'll just focus on this side of the molecule, and then I'll label the corresponding ones here. So this hydrogen at, this is about 5.02, is, well, also we have an N+1 rule. So you look on either side of the hydrogen. So we're only looking on this side, so you look on this side, we have no hydrogen, so the number of hydrogens plus 1 is how many peaks there is. So there's 1 peak, and this hydrogen right here is that one. So let's draw an arrow. This is at 5.02, 5.02. This is this hydrogen. Now, we have some symmetry here as well, where if you were to draw a line in the middle of this ring, you'd see that if you folded it, they'd be the same. So these hydrogens are going to be the same, and these hydrogens are going to be the same. Which this is the hydrogens in the benzene ring. So let's see which one's which. So this hydrogen right here is at around 7.49, which is, it's perfectly symmetrical here, you can see as well. So 7.49 is going to be this peak right here. So this hydrogen matches up with there. Let's draw the arrow to that one at 7.49. And then that means that this hydrogen right here is this one at 7.34. Actually have these hydrogens mixed up. This one is this one. And let's redraw this arrow right here at 7.34. Which means that when we look at the mirror image, this hydrogen is going to be this one. And this hydrogen is going to be that one. And this is the same on both sides. Here's our CNMR, and I've already drawn the structure here to get us started. Now we're gonna match these peaks to the structure, the different carbons in the structure. Now, I can already see, just like with the HNMR, it's symmetrical, so this only shows the one side. So let's put this line down the middle again. And this would be the carbons in the ring. Okay, let's get started. So I can see right here that this carbon at 60, about 70, 69, 70 is going to be this carbon right here because it is the least deshielded. Since there's no, it's surrounded by a hydrogen, a carbon, carbon, and a carbon. So this one's the least deshielded. So this carbon is this one right here. And actually, let's number these peaks. So it's gonna be peak. We'll go 1, 2, 3, 4, 5, 6. So this is carbon at 1. And that's at about, make a list right here, 1 is at about 70. Now 2 is gonna be this other carbon right here. Since we know that these are the ring, this carbon is the only carbon that could be. So at 2, that's at about 100. Let's put that right there and draw that arrow to it. Now we have the carbons in the ring. And this one is at about 128. So let's write our numbers right here with the corresponding location. 4, 5, and 6. So this one's at about 128. And then 4 is at about 130. 5 is at about 134. And 6 is at about 136. Okay. So let's see. And again, just like with the HNMR, this carbon, it's a little bit different. This carbon and this carbon is going to be the same, and this carbon is going to be the same, and these are two different. So let's see what this carbon's going to be. This carbon's going to be number 6. So let's draw that. This one's number 6. Let's bring that arrow. Actually, it's not number 6, it's number 5. This carbon's number 5 right here. And then let's just do the 2 carbons that we know are not going to be the same as another carbon. So this carbon right here, that one's going to be number 6 because it's the most shielded due to it being directly connected to that chlorine. So this one's number 6, this one's number 5, and we know we have 1 and 2. So let's see what this set of carbons is going to be, and then this set of carbons. This set of carbons is going to be number 3. And then this set of carbons is going to be number 4. So this carbon is 4, this carbon is 4, this carbon is 3, and this carbon is 3. And that's the same for both sides. So now, if we were to look at this side, we know that the carbon directly connected to the chlorine is number 6, and we know that the 2 carbons next to that are number 4. These 2 carbons are 3, and this carbon is 5. So we have our 1, 2, 3, 4, 5, and 6. And again, on this side, we have the 1, 2. We have our 3, our 4, our 5, and our 6. And that's for carbon NMR.